Welcome back to this channel. So in this video we are going to be starting Ionic Equilibria. Now Ionic Equilibria is a full topic under physical chemistry. So we are going to be looking at the first part of it, or the introductory part of it, before we go into ionization constants calculations. So this video is basically introducing the basic concepts of Ionic Equilibria. So this video is presented to you by Yusuf, and you're advised to subscribe to the channel and share the video to your friends so that you can all benefit as a family. In Equilibria, we are going to be looking at acids, bases, and salts. Now starting with acids and bases, we are going to be looking at acids and bases according to various people. Like we are going to be looking at Arrhenius and Bronsted mainly. So here we are saying that according to the Arrhenius theory, if at all we are to deal with acids and bases using Arrhenius theory or Arrhenius ideas, you will find that Arrhenius defined an acid as a substance that on dissolving dissociates to produce hydrogen ions in solution. So Arrhenius proposed that whenever you're having an acid, when you dissolve that acid in water or a solvent, which is basically water that we use, you only get hydrogen ions in solution as the only positively charged ions. So when you're having HCl, which is present in aqueous, HCl dissociates to form hydrogen ions and chloride ions. And nitric acid is going to dissociate to form hydrogen ions and nitrate ions. And sulfuric acid will form hydrogen ions and sulfate ions. However, Arrhenius proposed that also a base is going to be that substance which on dissolving in water is going to dissociate, but when it dissociates it's going to produce hydroxyl ions as the only negatively charged ions in the solution. So if you're having sodium hydroxide, it dissociates to form sodium ions and hydroxyl ions. And if you're having potassium hydroxide, it dissociates to form potassium ions and hydroxyl ions. Now we are saying that here, considering the reactions that have been said above, when a base is reacted therefore with an acid, if you react both a base and an acid, we form what we call a neutralization reaction. So neutralization occurs when you react a base and an acid. So hydrogen ions from an acid react with hydroxyl ions from the base, which are all present in the solution. That's why you're seeing aqueous to form water, and water is neutral to the litmus paper, both blue and red. That's why we call it a neutralization reaction. To be looking at acids and bases according to Bronsted theory. Now for Bronsted, he catered for some of the setbacks that Arrhenius left out in his theory. And Bronsted basically is the main concept that we consider in this topic according to advanced level. So Bronsted stated that an acid is going to be that substance that is going to donate protons to the base. So an acid is any substance that donates protons to a base. Therefore, if you're having hydrochloric acid in water and you dissolve it in water, this acid here is going to donate protons to this water, and then you form what you call hydroxonium ion, and then the chloride ions are also going to be left in solution. If you're having ethanoic acid, it reacts with water. What it does is that ethanoic acid donates protons to this water, which is acting as a base. And then we form the hydroxonium ions and then the ethanoate ion, which are all present in solution. That's why we are seeing the symbols being aqueous. Now going to the hydroxonium ion, we are saying that this is going to be called the hydrated proton, and its name is called oxonium or hydroxonium ion or hydronium ion. But here with NCDC, you are going to be going with hydroxonium ion. And it's also going to be referred to as the hydrogen ion. Now it's referred to as the hydrogen ion because we consider water to be in excess. So we don't consider water, and sometimes we just consider that hydroxonium ions are formed by getting a proton and adding it to a water molecule to form an hydroxonium ion. Now looking at the base, the concept of the base according to Bronsted, we are saying that a base is going to be that substance that accepts protons from an acid. Therefore, if you're having ammonia or aqueous ammonia solution, remember that ammonia is basic. So you say that a base is going to be that accepts protons from an acid. So that means that we need to add hydrogen ions on those basic compounds according to Bronsted theory. I told you, if you want to master this topic, make sure that you understand Bronsted theory very well, because it's all the calculations and all the interpretations are basically explained by Bronsted. So if you're having ammonia, reacting it with water, is that water donates a proton to ammonia, and then you form ammonium ions. But remember, all these ones are going to be reversible reactions. And then after water releasing one hydrogen ion, it's going to remain with oxide ion, hydroxide ion, in aqueous solution. Looking at example 4, we can also say that the amine of ethane, which is ethylamine, reacts with water, and this water donates a proton here. That's why you are seeing that after getting a proton, whenever something is basic, it picks a proton from water, and then water remains hydroxyl. Similar applies to ethanoate ions. It forms that. Now note that here, in reaction 1, water accepts a proton. If you look at reaction 1 here, we are referring to this. Water accepts a proton. I say that reaction 1 is here. Water accepts a proton from the hydrochloric acid and is going to form an hydroxonium ion. Water behaves as a proton acceptor, which is going to be a base. Now in reaction 4, which is present here, in reaction 4, water donates a proton to ethylamine, and by doing so it forms a thioammonium ion. And water here is behaving as a proton donor, which is present as an acid. So also note that strong acids and bases completely ionize in solution, whereas weak acids and bases partially ionize in solution. That's why we are using reversible arrows. Whenever you're having a weak base, all bases of organic compounds or all acids of organic compounds, you must be using reversible arrows, because for them we consider them as weak bases and weak acids. The only full arrows must be for strong acids like HCl, strong bases like sodium hydroxide, as we are going to be looking at as we proceed in this video. The idea of conjugate acids and bases, we are saying that benzoic acid, like I told you, anything having an organic name, either a base or an acid, they must be weak. That means that you have to use reversible arrows whenever you are representing such equations. So you are saying that here, benzoic acid ionizes in its aqueous solution according to the following equation. So when benzoic acid ionizes in solution, it forms benzoate ions and hydroxonium ions. Now here you are saying that in the equilibrium above, the benzoate ion is a conjugate base. It's a conjugate base of benzoic acid, and you're saying that benzoic acid is going to be the conjugate acid. Reason being, if you're looking at the benzoic acid donated protons to water, and by doing so it becomes an acid. That's why we call it a conjugate acid. And then after forming the ethanoate ion, we call that one what is being formed after donating a proton, we call it a conjugate base of benzoic acid. And the two form a conjugate acid-base pair. Now furthermore, we are saying that the conjugate base is going to be formed when an acid loses a proton. So that's how we form a conjugate base. If you're having benzoic acid and benzoic acid loses a proton, what is being formed after loss of an electron is called a conjugate base. The product formed after loss of a proton is called a conjugate base. Now the reactant that is losing the reactant that is losing the proton, or that is donating a proton or an hydrogen ion, is called the conjugate acid. And you're saying that when the conjugate base gains a proton, it forms back the conjugate acid. If you add a proton here to this ethanoate ion, we shall form back our ethanoic acid or benzoic acid. That means that we shall be forming back our conjugate acid. Remember that a conjugate acid is that one that is going to donate a proton. Now a conjugate base is that base that is formed after donation of a proton, or is that compound that is formed after donation of a proton by a conjugate acid. Now proceeding, we are saying that the acids and bases can therefore be neutral molecules, positive ions or negative ions. Now here are examples of the acid-base pairs, and they include the following. So here we are going to look at the conjugate acid. By saying conjugate acid is going to be that compound or a substance that is able to donate protons. And the conjugate base is going to be the compound formed after our conjugate acid has donated off its protons. So the conjugate acid here is going to be HCl. After HCl donating its protons, we form what we call a conjugate base, and in this case is going to be chloride. Here we have nitric acid. After donating off one proton, it forms nitrate ion, and this is our conjugate base. If you look at sulfuric acid will donate off one proton or an hydrogen ion, and it will form hydrogen sulfide or hydrogen sulfate, which is going to be our conjugate base. So you have to understand that a conjugate base is a compound formed after loss of one hydrogen ion, and then a conjugate acid is going to be that compound that is ready to release hydrogen ions in solution. So if you're having hydrogen sulfate, after hydrogen sulfate releasing its proton, it forms a sulfate ion, and this is going to be our conjugate base. If you're having hydrogen sulfide, it loses off one proton, it forms hydrogen sulfide. And if you're having hydrogen sulfide, it loses off one proton, it forms the sulfide ion. If you're having ammonium compound, it loses one proton, it forms ammonia. Now ammonia becomes our conjugate base, and the ammonium ion is going to be our conjugate acid. So repeating this, I say that a conjugate acid is going to be that compound releasing a proton in solution. And the conjugate base is going to be that compound that is formed after release of a proton in solution. Here, let's proceed with the classification of strong acids and bases. We also look at weak acids and bases. Now, if you look at a strong acid, just like you defined it in your O-level, this is going to be an acid which ionizes completely. The keyword here is going to be completely, ionizing completely in its aqueous solution. And therefore, if something is able to ionize completely, it's going to release many protons. And if you are to compare it with the weak acid, we shall be saying that here weak acid is going to be that acid which just partly. Now what differentiates this one from this one is that weak acid just partly or partially ionize in their aqueous solution, and therefore they do not easily release their protons. By protons we also mean hydrogen ions. So a weak acid is going to be that acid that just partially ionizes in aqueous solution, in its aqueous solution, to give off very few hydrogen ions. Whereas a strong acid is going to be that acid that fully ionizes or that completely ionizes in its aqueous solution to form very many hydrogen or protons in solution. So looking at the examples of strong acids are here and examples of weak acids are here. So one of the examples of a strong acid, you are going to be looking at hydrochloric acid, we are going to be looking at hydrobromic acid, you are going to be looking at hydroiodic acid, and we shall be looking at nitric acid. We look at sulfuric acid, and then chloric 7 acid. These are some of the strong acids that you are having in physical chemistry or in chemistry in general. And then weak acids, mainly weak acids are going to be for organic compounds. So ethanoic acid, methanoic acid, hydrosanic acid, hydrofluoric acid, butanoic acid, and carbonic acid. So these ones are classified under weak acids. So looking at a strong base, we are going to define a strong base as that one which ionizes completely in its aqueous solution and easily accepts protons. We consider Bronsted-Lowry's theory to define these statements. So strong base is going to be that base. First of all, being strong, it means that means the word strong implies that is full ionization or complete ionization. So it's going to be that base which ionizes completely in its aqueous solution, and therefore it's always going to easily accept protons. And if you look at a weak base, weak, that means that it means partial ionization. So weak base is a base which partly ionizes in its aqueous solution, and therefore, since it partly ionizes, it means that it's not going to easily accept protons. Examples of strong bases and strong acids, we are going to, under strong bases, we have potassium hydroxide, sodium hydroxide, barium hydroxide, and lithium hydroxide. And looking at weak bases, we are going to be looking at aqueous ammonia, aqueous methylamine, aqueous phenylamine, and aqueous triethylamine. Now looking at the relative strength of Bronsted-Lowry's acids and bases. Now we are going to be saying that the strength of different acids in aqueous solution under similar conditions are going to be predicted by their degrees of dissociation. Degree of dissociation is represented by alpha, as we looked at that in chemical equilibria. And then the acid dissociation constant. Acid dissociation constant is written by capital K and a subscript of A. And then the base dissociation constant is written by capital K and then a subscript of B. So this B implies for a base, and this A implies for an acid, and the K is read as ionization constant. So alpha implies degree of dissociation of any acid or any base. Ka is going to show that this is going to be ionization constant for an acid. And then Kb is going to show that this is going to be ionization constant for a base. Now looking at the note, we are saying that inductive effect, the definition of an inductive effect, just like we looked at it in chemical kinetics, we are going to be repeating that here. Inductive effect is going to be that ability of an atom or a group of atoms to donate electrons towards a neighboring atom, or the ability to withdraw electrons from the neighboring atom. So inductive effect is divided into two. We have positive inductive effect, just like we are going to be looking at the example questions to master this properly. And then we have the negative inductive effect. So for positive inductive effect, they are the ones that donate electrons to the neighboring atoms. And for negative inductive effect, they are the ones that withdraw. Negative means you are demanding. So negative inductive effect, they are the ones that withdraw electrons from the neighboring atoms. Positive inductive effect, it means that they are the ones that give electrons to the neighboring atoms. Of the questions that are going to help us understand fully what ionization constant, degree of dissociation of either an acid or a base literally imply. Now what you should note here, that the degree of ionization constant, just like you are hearing ionization constant, the higher the ionization constant, that means that that acid is very strong. If the ionization constant is high, that means that the acid can easily ionize in solution to give off very many protons in the solution, and that means that that's going to be a strong acid. And if the ionization constant is low, the acid is going to be ionizing less in solution, and therefore that such a solution is going to contain very few hydrogen ions. And by so, that means that we shall be having a less strong acid or a weak acid. Now if you look at the table below, it's going to show the acid dissociation constants, which is noted by Ka, K subscript A of group 7 hydrates. Now if you look at the hydrates, we have hydrogen fluoride, we have hydrogen chloride, and hydrogen bromide, hydrogen iodide. And then the ionization constants is measured, or is ionization constant of an acid and a base are measured in moles per decimeters cubed. Now this is very important because in paper 1, we ask you for the units of the acid dissociation constant or the base dissociation constant. Just to remind you, I say that acid dissociation constant is denoted by capital K and then small a. And then the base dissociation constant is denoted by capital K and then the subscript of B. Now at 25 degrees Celsius is the room temperature, and it's trying to tell you that the experiment was carried out at a room temperature. So hydrogen fluoride has its acid dissociation constant to be 6.6 exponential -4. Hydrogen chloride is 1.3 exponential 6. hydrogen bromide is 1 exponential 9, and hydrogen iodide is 3.2 exponential 9. Now if you look at the one which has the highest ionization constant, is going to be hydrogen iodide, followed by hydrogen bromide, followed by hydrogen chloride, and lastly hydrogen fluoride. Now let's look at the reasons why it's in that way. Now explaining the trend of the ionization constant value of the hydrides, we are going to say that the ionization constant Ka values are going to increase in this order: hydrogen fluoride, acidity of hydrogen fluoride, or the ionization constant of hydrogen fluoride is less than that for hydrogen chloride, and that for hydrogen chloride is less than that for hydrogen bromide, and that for hydrogen bromide is less than that for hydrogen iodide, therefore indicating that acid strength increases in the same order. Now the strength of an acid, first of all, before explaining strength of acids, you have to first state what are the factors affecting strength of an acid. In every statement that you make, or in every acidity explanation that you are supposed to give, you have to first state the factor that affects the strength of the acid. And this is the sentence that we started with after stating our trend. And we say that the strength of an acid is going to depend on how easily it is to release protons in solution. So we have stated the factor that affects the strength of our acids. Now you can go ahead with explanations. And you're going to be saying that this is because if you look at the atomic radius of the halogen atoms, by halogen atoms I mean fluorine, chlorine, bromine, and iodine. So if you look at the atomic radius of the halogen atoms, it's going to be increasing from fluorine to iodine. That means that hydrogen iodide, the length of the bond between hydrogen and iodine is going to be long, because this iodine here to bond with hydrogen, its atomic radius is very big. So that means that the bond is long, and we say that when the bond is long, it makes it weak. And if the bond gets weaker, it is easily broken in solution to release very many protons. But if you look at fluorine has the smallest atomic radius. So that means that the bond between it and hydrogen is going to be very short. And we say that the shorter the bond, the more stronger it is. Therefore, hydrogen fluoride, we expect it not to easily release its proton in the solution. And if we also look at hydrogen fluoride, the hydrogen fluorine bond, we call it a hydrogen bond. Remember that we said that hydrogen bonds are formed between fluorine and hydrogen, oxygen and hydrogen, and also nitrogen and hydrogen. It's 3 atoms. If fluorine bonds with hydrogen, we form what we call an hydrogen bond. If oxygen bonds with hydrogen, we form what we call an hydrogen bond. And if nitrogen bonds with hydrogen, we form what we call an hydrogen bond. Now such bonds are the strongest in chemistry. Hydrogen bonds are the strongest bonds that we are having in chemistry. And therefore, anywhere they are formed, if they are very strong, that means that it's very hard to release protons in solution. So looking at this further, we are going to be saying that we say that this is because the atomic radius of the halogen atoms increases from fluorine to iodine, and then we proceeded by saying that this is going to make the hydrogen to halogen bond length longer. Once it becomes longer, it reduces the bond strength, and the bond strength is going to be progressively decreasing from hydrogen fluoride to hydrogen iodide, or to hydrogen iodide bonds. You can explain them in terms of bonds, releasing very many hydrogen ions in solution. Just like I've explained, hydrogen iodide has the largest atomic radius. Because the iodine atom has the largest atomic radius, the bond is going to be longer. Once it's longer, it becomes weaker. Once it becomes weaker, it becomes easy for the hydrogen iodine bond to be broken, as compared to the hydrogen fluorine bond. So we are looking at an anomaly of hydrogen fluoride or hydrofluoric acid, and we are saying that hydrofluoric acid is going to be the weakest acid because the fluorine atom has the highest electronegativity due to its very small atomic radius. And being that it has a very small atomic radius, the hydrogen to fluorine bond is going to be highly polar and very strong, making the acid to dissociate considerably at a small extent. And I told you hydrogen to fluorine bond is called an hydrogen bond. And also small atomic radius forms a shorter bond. Shorter bonds are highly polar and they are very strong. Hence it's very hard for protons to be released in solution for such an acid, which makes hydrofluoric acid the least strong acid with the lowest ionization constant. Example 2, we are going to be looking at acid strength of oxy-ions or oxy compounds. So we call these ones oxy-acids, compounds that have oxygen atoms in them and they are at the same time protons. So if you look at hydrogen ions and oxygen atoms present in a compound, we call those ones oxy-acids. So we are looking at oxy-acids of the chlorine, increasing the order least. So the acid strength of the oxy-acids of chlorine atoms increases in this order. Now whenever you see such, they are trying to bring in the concept of inductive effects. Now when you're looking at inductive effects in the previous videos, also organic chemistry, we say that now oxygen atom is going to be causing the number of oxygen atoms present, they cause what we call a negative inductive effect. That means that they withdraw electrons towards themselves. If you look at this compound here, it has been indicated by arrows, showing that electrons are being pulled to the oxygen atom because the oxygen atom is more electronegative than this chlorine atom. So it pulls away the lone pairs of electrons from chlorine to itself. And then what chlorine does, it also pulls away electrons from the hydrogen to oxygen bond. Now, by pulling away electrons from the hydrogen to oxygen bond, it makes the hydrogen to oxygen bond weaker or highly polar. That means that the oxygen atom is going to have a high partial negative and the hydrogen atom is going to have a high partial positive. Now, once this happens, it weakens the hydrogen to oxygen bond, and therefore that means that in solution, this bond can easily break to release these protons in solution. And now the extent of the negative inductive effect is going to increase by increasing the number of oxygen atoms. So you see now the effect is now increasing, that this chlorine atom, there are two oxygen atoms that are taking away electrons from it. That means that the polarity of the hydrogen to oxygen bond is going to increase. The partial negative is going to be more steeper on oxygen, and the partial positive on hydrogen is also going to be more steeper. Now once that happens, this weakens the hydrogen to oxygen bond, making this bond to easily be broken to release protons in solution. As you can see here, when the more increased oxygen atoms attached to the chlorine atom, the more increased negative inductive effect, which is the ability for the oxygen atom or for any group of atoms to withdraw electrons from another atom. A group of atoms. The more they withdraw electrons here, the more they cause polarity in the oxygen-hydrogen bond. And the more polarity is caused in the oxygen-hydrogen bond, the weaker the oxygen-hydrogen bond becomes, making it easily release protons in solution. So by that, we can conclude that the higher the number of oxygen atoms present in any oxy-acids, the stronger that acid is going to be. Because we say that acid strength depends on how easily or how easy it is to release protons in solution. So the ease by which protons are going to be released in solution is going to increase with increase in the number of oxygen atoms, since they are going to increase what we call negative inductive effect. And therefore with that, let's come up with a detailed explanation, and let's go through with what I summarized. So you're saying that here, the strength of an acid depends on how easily it is to release protons in solution. That's the factor before you start explaining. Now here we didn't state the trend because the trend was given to us in the question. So what you had to do here is just to start right away in explaining. But before starting to explain, you have to say the factor by which the acid strength depends on. So here we are going to be saying that the strength of an acid depends on how easily it is to release protons in solution. And we are saying therefore that the acid strength increases depending on the number of oxygen atoms that exert a negative inductive effect in each molecule of an acid. And we are saying that the more the oxygen atoms present in an oxo-acid, that means that we are going to be increasing polarity of the oxygen-hydrogen bond, just like I've explained earlier on. And we are saying that this is because the oxygen is going to be more electronegative than chlorine. And since oxygen is more electronegative than chlorine, it withdraws these electrons toward itself, just like I represented them with those arrows. So this is because oxygen is more electronegative than chlorine, and by doing so, we are saying that in chloric 7 acid, 3 oxygen atoms exert a negative inductive effect, which is greater than others, because the more, remember that oxygen is exerting a negative inductive effect. That means that the more the oxygen atoms, the greater the extent of the negative inductive effect. So 3 oxygen atoms exert a negative inductive effect on the oxygen to hydrogen bond, making it very weak, and therefore it's going to break easily to release very many hydrogen ions, making it a stronger acid than other acids, like than chloric 5 acid, which has only 2 oxygen atoms, because the one which has only 2 oxygen atoms is going to be exciting slightly lower. It's going to be slightly lower. Its ionization constant is going to be slightly lower than that which has 3 oxygen atoms. I've told you, negative inductive effect is going to increase with increase in the number of oxygen atoms. So that means that an oxo-acid that has the highest number of oxygen atoms is going to have the highest acidity, as compared to that one which has very few oxygen atoms. So making the oxygen to hydrogen bond weaker than in chloric 3. And by doing so progressively, we reduce what we call acidity. Now we are saying that in chloric 1 acid, it has the strongest oxygen to hydrogen bond. And why is it the case? If you look at chloric 1 acid, which is here, up here, chloric 1 acid only has 1 oxygen atom, or it doesn't have any oxygen atom which is attached to this chlorine atom. That means that this chlorine atom does not have any oxygen atom to make it, or there is no negative inductive effect in this component, and that means that the polarity between this one and this one is less. That means that the hydrogen to oxygen bond is going to be very strong, and it's going to be very hard for this bond to be broken to release these protons in solution. And once it's very hard to release these protons in solution, it makes such an acid a very weak acid. So we are saying that the chloric 1 acid has the strongest oxygen to hydrogen bond because no oxygen atom has a negative inductive effect in it, and therefore the oxygen to hydrogen bond is very strong. It's very hard for that bond to break in aqueous solution to release the protons, and therefore, since acid strength depends on how easy it is to release protons in solution, such an acid is going to be called a weak acid. Here we are going to be looking at an example of what we call the effect of positive inductive effect in different compounds. Now here, if you look at these compounds, all of them, the carboxylic acids that are given, they all have the same constant thing. And once something is constant, you remove your focus on it. So there's nothing like negative inductive effect because you have seen the oxygen atoms, because oxygen atoms are present on each compound. So we find which other thing is varying. So if you are trying to find which other thing is varying, you find that the atoms or the group of atoms attached to the carboxyl group is varying. Here hydrogen is attached to our carboxyl group, and here is the methyl group which is attached to our carboxyl group, and here is the ethyl group which is attached to our ethyl group. This is propanoic acid, this is ethanoic acid, and this is methanoic acid. Now the acid ionization constant, which ionization constant I told you is measured in moles per decimeter cubed. So that the one for methanoic acid is 1.77 exponential negative 4. The one for ethanoic acid is 1.70 exponential negative 5. And the one for propanoic acid is 1.3 exponential negative 5. Now let's state and explain the trend of the acid strength according to the ionization constants given. Now the acid strength is going to decrease in the order. If you want to say increase, when you're saying increase, you make sure that you use less signs. When you're saying decrease, you make sure that you use greater signs. So acid strength decreases in the order ethanoic acid being greater than ethanoic acid and being greater than propanoic acid. Now I told you before explaining anything like acid strength or anything related to acid strength, you have to first state the factor at which acid strength depends on. And if you look at that, we are saying that acid strength depends on how easily it is to release a proton. So that's your first thing before you start explaining. Now let's first talk about positive inductive effect briefly. In the previous question, we have been talking about negative inductive effect, and you have seen that the negative inductive effect takes away electrons from our oxygen to hydrogen bond. If you look at carboxylic acids, they have this group, which is the OH group, which we are also explaining before. But in the previous, where we had the negative inductive effect, you have been seeing that protons were being taken away from this bond. The more protons were taken away from this bond, the more this bond became weaker. Now for positive inductive effect, we donate protons. Now the more we donate protons to this oxygen to hydrogen bond, the stronger it becomes. And the positive inductive effect here is going to be increasing with increasing the number of carbon atoms that are present in our alkyl groups. So that means that the methyl group has a positive inductive effect, but the ethyl group is going to have a more positive inductive effect as compared to the methyl group, because in the ethyl group we're having 2 carbon atoms, and those 2 carbon atoms, they're going to donate more protons this bond, as compared to the methyl group, which has only 1 carbon atom to donate protons to this bond. So that means that propanoic acid is going to be weaker than methanoic acid or ethanoic acid, because if you look at propanoic acid, 2 carbon atoms will provide more electrons. The more they provide electrons to this bond, the stronger this bond gets. So that means that propanoic acid is a weaker acid because it has the highest positive inductive effect. It donates more protons to the oxygen-hydrogen bond. The more it donates electrons to the oxygen-hydrogen bond, the stronger it gets, because it will be reducing the partial negative on oxygen and it will be reducing the partial positive on hydrogen, or it will be reducing polarity of the oxygen to hydrogen bond. But in methanoic acid will have a less positive inductive effect because it has only 1 carbon atom in its alkyl group, which is methyl group. So since 1 carbon atom is present, there will be a less positive inductive effect on the oxygen to hydrogen bond. Few electrons will be given. Therefore, this bond is going to be slightly weaker to release slightly higher number of hydrogen ions in solution as compared to that in propanoic acid. Now looking at methanoic acid, talking about methanoic acid alone, methanoic acid does not have an alkyl group. It just has the hydrogen atom which is attached to the carboxyl group, and this hydrogen atom does not have any inductive effect. It doesn't exert either positive or negative inductive effect. So that means that here methanoic acid is going to be the strongest, because methanoic acid does not have any negative or positive inductive effect on the oxygen to hydrogen bond. Now if that's the case, that means that this bond is going to be the weakest across the compounds that were given to explain, and since it's the weakest, it will be easily broken in solution or in its aqueous solution to release these protons in solution. And the more it releases protons in solution, the stronger that acid becomes, or the stronger that acid is considered. Now we are saying that the strength of an acid is going to depend on how easily it is to release a proton, and we are saying that methanoic acid has an hydrogen atom instead of an alkyl group attached to the carboxyl group, and we are saying that that hydrogen atom does not have any inductive effect, and therefore the oxygen to hydrogen bond in it is going to be the weakest. And since it's the weakest, it's going to easily break to release many hydrogen ions in solution. Now we are saying that here, the alkyl groups that are present in ethanoic acid and propanoic acid have a positive inductive effect. Now we are saying that the positive inductive effect decreases polarity of the oxygen to hydrogen bond, making it not easy to be broken. And we are saying that the strength of the oxygen to hydrogen bond is going to increase as positive inductive effect increases. That means that propanoic acid has the highest positive inductive effect because it has 2 carbon atoms in its ethyl group. That the more the number of carbon atoms in the alkyl group, the higher the positive inductive effect. And the higher the positive inductive effect, the stronger the oxygen to hydrogen bond and the weaker that acid is. So you're saying that the strength of the oxygen to hydrogen bond increases as the positive inductive effect increases, with increase in the number of carbon atoms that are present in the alkyl groups, which are attached to the carboxyl group. Let me hope you understood this explanation very well, because these questions are very common in the UNEB papers. Looking at number 4, we are going to be looking at the table that shows the acid dissociation constants Ka for some acids that are present at a particular temperature. Now acids, we are going to be looking at methanoic acid. We look at this acid which has the chlorine atoms. Now whenever you see chlorine atoms, notice that chlorine atoms, always for them they have a negative inductive effect. Alkyl groups always have a positive inductive effect. Always master it that way, that whenever you see halogen atoms, they have a negative inductive effect. And alkyl groups like the methyl, ethyl, propyl are going to have a positive inductive effect. So the acids are as follows. And their acid dissociation constant, I repeat, acid dissociation constant is written as capital A with a subscript of A. And then the acid dissociation constant is measured in moles per decimeters cubed. The values for that is going to be 1.7 exponential negative 5, 1.5 exponential negative 3, 5.1 exponential negative 3, and then 2.2 exponential negative 1. Now here we are, first of all, we are going to state and explain the trend in the acid strength of the acids, of the individual acids. Now the trend is going to be in this way. I say that when you are going to use the word increase, always make sure that you use less signs. This one is less than this, is less than this. If you are going to use decrease, then you are supposed to use greater signs. Now we are saying that here, the acid strength is going to increase in the order of this. So the first acid is going to be less stronger than this, and then it's going to be less stronger than this, and then it's going to be less stronger than this. Now here we are saying that I told you before explaining anything related to acid strength, you have to first state the factor at which that acid depends on. And you're saying that the strength of an acid is going to depend on how easily it is to release a proton in solution. Now if you look at ethanoic acid, I've told you that alkyl groups have a positive inductive effect, and in the previous question we saw that positive inductive effect strengthens the oxygen to hydrogen bond. That means that hydrogen ions cannot be easily released in solution, which makes such an acid a very weak acid. And if you look at compounds that have a negative inductive effect, the more the number of atoms that have a negative inductive effect in a particular compound, the stronger that compound, the stronger the acidity of that compound, because for them they have a negative inductive effect. That's why we are saying that here ethanoic acid has a methyl group, and this methyl group is attached to our carboxyl group. Now the methyl group has a positive inductive effect, hence its oxygen to hydrogen bond has the lowest polarity, making it very strong, and therefore is not going to easily break in solution to release hydrogen ions. And if a compound cannot easily release hydrogen ions in solution or protons in solution, it makes it a very weak acid. The strongest acids are those ones that can easily release protons in solution. Now going to chlorine, we are saying that the chlorine atoms in chloroethane, chlorine atoms in chloroethanoic acid and dichloroethanoic acid and trichloroethanoic acid are more electronegative than carbon. Therefore, they are going to exert a negative inductive effect, which is going to increase the polarity of the oxygen to hydrogen bond. Now, once they increase the polarity of the oxygen to hydrogen bond, it makes the oxygen hydrogen bond very weak to break. And if it's very weak to break, that means that hydrogen ions are going to easily be released in solution. That's why we are saying that making it weak and easy to break. Therefore, the strength of the oxygen to hydrogen bond is going to decrease as the negative inductive effect increases. And we say that what increases the negative inductive effect is going to be the number of atoms that exert it. When you're looking at the first question or the second question, we saw that oxygen was the one which is, the more increased oxygen atoms, the more increased the negative inductive effect. And here we look at chlorine instead of oxygen. So the more chlorine atoms are there, the more the negative inductive effect increases. And once the negative inductive effect increases, our oxygen to hydrogen bond becomes less polar. or it becomes very weak to break. So that's why we are saying that here, once it becomes very easy to break, protons are going to easily be released in solution, and once they're easily released in solution, it makes such a compound or such an ion or such a compounded substance be a strong acid, because it can easily release protons in solution. So the strength of the oxygen-hydrogen bond decreases as the negative inductive effect increases. A negative inductive effect increases with increase in the number of chlorine atoms that are present in the chain, which are attached to the carboxyl group. Now looking at the table below, or question 5, question 5 is going to show acid dissociation constants Ka for some acids at a particular temperature. Now since I've already addressed all these concepts, we're just going to be going through this one, since we have already understood the basic concepts. So state and explain the acid strength of the acids given above. So here, ethanoic acid is going to be the weakest acid, because if you look at ethanoic acid, it has the methyl group. The methyl group has a positive inductive effect. Now if you look at these other groups, they are having halogen atoms. Now, but these halogen atoms, what is going to vary here is going to be the atomic radius of the halogen atoms. So let's look at that briefly. So you're going to say that for the other acids, acid strength is going to decrease in this order. Fluorine is going to be greater than this, and it's going to be greater than this, and it's going to be greater than this. Now the strength of an acid is going to depend on how easily it is to release a proton. I said that before starting to explain, already state the factor at which the strength of an acid depends. Now you're saying that ethanoic acid has a methyl group attached to the carboxyl group, and the methyl group or alkyl groups always have positive inductive effect. Now by having positive inductive effect, the oxygen to hydrogen bond in them is going to have the lowest polarity, and hence is going to be stronger. Hence it does not easily break in aqueous solutions to release hydrogen ions, making it the weakest acid. But however, for the other compounds which have halogen atoms, which we can call halogen substituted acids, the halogen atoms are more electronegative than the carbon atom, and therefore a negative inductive effect is going to be exerted in such compounds. So however, the negative inductive effect is going to decrease with the decrease in electronegativity. That means that fluorine, which has the highest electronegativity, is going to be more acidic as compared to others. So negative inductive effect decreases with a decrease in electronegativity, and that happens from fluorine to iodine. And once we do so, we decrease the polarity of the oxygen to hydrogen bond, making it very hard or not easily break. The oxygen to hydrogen bond does not easily break in solution to release protons to the solution. Therefore, fluoroethanoic acid is the strongest acid, and iodoethanoic acid is going to be the weakest acid. We're going to be looking at acid. Now this is not acid, it's going to be base dissociation constants. Instead of acid, cross it out and you make it base dissociation constants, which you call the Kb values. Now here I'm saying that here, the strength of the weak bases are going to be compared using more conveniently. They're going to be compared using more conveniently by use of their base dissociation constants. The higher the base dissociation constant, the stronger the base. And then electron withdrawing groups, or groups that have a negative inductive effect, are going to make our bases weaker by making their own pairs of electrons that are available on those particular atoms that determine basicity to be less available to accept protons. Now electron donating groups, or groups that have a positive inductive effect, make our bases stronger by making their own pair of electrons readily available to accept protons. So here is the table below, and we are going to be explaining the trend in the base dissociation constants according to various questions. So pause the video and you write down this question. However, when you're writing down this, you notice that here in ammonia we don't have any ethyl group attached. In triethyl amine we have three alkyl groups. Here we have one alkyl group attached to the nitrogen atom, and here we are having one alkyl group attached to the nitrogen atom but having two carbon atoms. And I told you positive inductive effect is exerted by alkyl groups. The more the number of alkyl groups, the higher the positive inductive effect. And the more the number of carbon atoms in an alkyl group, the higher the positive inductive effect. So you're also having this, you're also having this, you're also having this. Now let's look at a brief explanation of the items. Comparing and explaining the basic strength of ammonia, methylamine, and ethylamine. Like I told you here, alkyl group is methyl and it has only one carbon atom. And here, the alkyl groups is ethyl and it has two carbon atoms. And we say that alkyl groups exert a positive inductive effect. The strength of the base depends on the availability of lone pairs of electrons on the nitrogen atom to accept protons from an acid or from a solution. Positive inductive effect acts to donate protons to the nitrogen atom. So the greater the number of carbon atoms in the alkyl group, the more electrons are going to be readily available on the nitrogen atom to accept protons from the solution. And therefore, we are going to consider that one to be highly basic or a strong basic solution. If you look at the methylamine, one carbon atom is present in the alkyl group, few electrons are going to be presented. That means that it's going to be a weaker base compared to this one, because few electrons are already available to accept protons from the solution. If you look at ammonia, there is no alkyl group attached to it. It is only attached to hydrogen atoms, and they say that hydrogen atoms do not have any inductive effect, either negative or positive. So that means that on nitrogen atom, there are very few lone pairs of electrons available to readily accept protons from the solution. So that's why we give a basic. Before explaining any strength of either base or an acid, state the factor to which it depends on. Now for basic or for bases, the basic strength is going to depend on the availability of lone pairs of electrons that are present on the nitrogen atom to accept protons. Now you are saying that here ammonia is going to be the weakest base because the hydrogen atoms attached to the nitrogen atom have no inductive effect, like I've explained. Now the alkyl groups that attached to the nitrogen atom in both methylamine and ethylamine have what we call a positive inductive effect. Now having that positive inductive effect, I told you positive inductive effect refers to those groups of atoms that donate electrons. Now those electrons that are donated are going to be going to the nitrogen atom. That means that their lone pairs of electrons are going to be readily available in the nitrogen atom to accept protons from the solution. So that's what we are explaining here. And we're saying that in methylamine and ethylamine, they have a positive inductive effect which increases the electron density on the nitrogen atom, making the lone pairs of electrons to be readily available to accept protons, or what you can say as for protonation. Now the positive inductive effect is going to increase with increase in the number of carbon atoms that are present in the alkyl groups. That means that ethylamine has a greater positive inductive effect as compared to methylamine. And therefore we can conclude that ethylamine is going to be a stronger base as compared to methylamine. Looking at comparing and explaining the basic strength of methylamine, dimethylamine, and trimethylamine. So basic strength increases in this order. I've told you the alkyl groups here. The increase in the number of alkyl groups is going to increase basic strength. But however, there is an abnormality with the amine, which is tertiary. So here we say that increases in this order, this one, and this one, and you're going to be explaining it according to the following explanation. As we are saying that the basic strength of amines is going to depend on the availability of lone pairs of electrons on the nitrogen atom. Having said that, we start our explanations. Now the theory, let's first explain this abnormality of this one. The three methyl groups attached to the nitrogen atom in trimethylamine, they have the greatest positive inductive effect. Now, having had the greatest positive inductive effect, we expected it to be the strongest base. But however, due to steric hindrance, when we say that steric hindrance, we mean that the methyl groups are attached they form a cloak, like they entangle all this nitrogen atom in such a way that they resist the lone pairs of electrons that are present to accept protons. That's what we say by steric hindrance. The three methyl groups, they oversurround the nitrogen atom, giving it no breathing space for lone pairs of electrons to accept protons. So we are saying that, but due to steric hindrance to the approach of protons towards the nitrogen atom and the poorest solvation. Now solvation is the same as hydration. Poorest solvation or hydration due to lack of nitrogen to hydrogen bonds. Trimethylamine is going to be the weakest base. It has the greatest positive inductive effect, but here it provides no breathing space for lone pairs of electrons, or it does not allow lone pairs of electrons that are present on the nitrogen atom to accept protons due to poor solvation or due to poor hydration. And therefore, that qualifies trimethylamine to be a weakest base. However, when you have to compare this one and this, and also the lack of nitrogen to hydrogen bonds. So if you have to compare the methylamine and dimethylamine, we are going to be saying that the methyl groups that attach to the nitrogen atom in methylamine and the methylamine, they also have a positive inductive effect, and the positive inductive effect increases with increase in the number of alkyl groups attached to that nitrogen atom. So since they have a positive inductive effect, the purpose of the positive inductive effect is to increase the electron density that is present on the nitrogen atom, making lone pairs of electrons readily available for protonation. However, methylamine and methylamine also have the nitrogen to hydrogen bonds that gives them a high solvation, unlike in trimethylamine. If you look at trimethylamine, it didn't have any hydrogen bond anywhere, which makes it the weakest base still. For something to be a good base or a strong base, it must have the nitrogen to hydrogen bond. And after that is the nitrogen to hydrogen bond, it must be attached to either one alkyl group or other alkyl groups. So you're saying that here, dimethylamine also have nitrogen to hydrogen bonds, which increases their solvation. I said that solvation is the same as hydration. When they ask you for solvation energy, in chemistry, they also is the same as asking you for hydration energy. So you're saying that the positive inductive effect and the solvation or hydration increases with the increase in the number of alkyl groups that is being attached to the nitrogen atom directly, and the number of the nitrogen to hydrogen bonds respectively present. Hence, dimethylamine is going to be a stronger base as compared to methylamine. This is concerned with the benzene rings, and you're saying that here you are going to be comparing and explaining the basic strength of ammonia, ethylamine, and aniline. Now notice that in aniline, we have a benzene ring attached to our amine or the nitrogen atom. Whenever you're talking about bases, we talk about availability of lone pairs of electrons on the nitrogen atom. We only talk about that. And what determines the availability of lone pairs of electrons on the nitrogen atom is going to be either positive inductive effect about the group it is attached to, or the negative inductive effect about the group or the groups it is attached to. So looking at the basic strength of amines, we are going to say that they are going to depend on the variability of electrons that are present on the nitrogen atom. Now in aminobenzene, or aniline is going to be the weakest base, because lone pairs of electrons that are present on our nitrogen atom, they are going to be interacting with the delocalized pi electrons that are present within the benzene ring. Now what happens is that this reduces the electron density that is present on the nitrogen atom, and once the electron density present on the nitrogen atom is reduced, it makes lone pairs of electrons that are available now on the nitrogen atom to be less available for protonation or to accept protons. Now ammonia is going to be the strongest base than aminobenzene, because for the nitrogen atom in ammonia is only attached to hydrogen atoms, and just like earlier said, hydrogen atoms do not have any inductive effect. Ammonia also has more nitrogen to hydrogen bonds as compared to aminobenzene, and therefore it's going to have the highest solvation energy or highest solvation than aminobenzene. Now if you look at ethylamine, the ethyl group attached to the nitrogen atom has a positive inductive effect, and we are going to say that which increases the electron density. For positive inactive effect, they donate electrons towards the nitrogen atom, and by doing so they increase the electron density that is present on the nitrogen atom. And once this happens, it makes the lone pairs of electrons present on the nitrogen atom to be easily available for protonation. That means that ethylamine is going to be a relatively stronger base. Now, taking a note here that amides are negligibly basic or neutral in aqueous solution as compared to aliphatic amines presented by this formula, because lone pairs of electrons on the nitrogen atom in amides always interacts with the localized electrons that are present in the carbonyl group, and those electrons are always for the carbon atom in the carbonyl group, and therefore they are going to make those electrons less available for protonation. We are explaining why ethylamine is going to be a stronger base than ethanamide, or represented by this formula. So this is called ethanamide. Although both compounds have an amino group. Now here you're saying that the ethyl group attached to the nitrogen atom in ethylamine is going to have a positive inductive effect, just like we have been explaining. Therefore, as a result, it's going to increase the electron density present on the nitrogen atom, making the lone pair of electrons readily available for protonation. However, in ethanamide, the lone pair of electrons on the nitrogen atom, they are going to interact with the pi electrons that are present in the carbonyl group. By carbonyl group, I mean this group that shows presence of a carbonyl compound. So pi electrons, they interact with lone pairs of electrons on the nitrogen atom interact with the pi electrons that are present on the pi electrons of the carbonyl group, therefore making the lone pairs of electrons present on the nitrogen atom less available for protonation. And this is given around 3.5 marks or 4 marks for explanation. End of this video, or the first introductory video for ionic chemistry or ionic equilibria. Now we are going to be proceeding with calculations in the upcoming videos about ionic equilibria. Now, just like earlier emphasized, you share the video to your friends and you like the video so that you can all benefit as a family.